All right, in this section, what we're going to do is introduce some rules of derivatives that'll serve as like shortcuts. They're going to be techniques to find a derivative so that we don't have to set up the limit every time. So this is going to make quick work of some of the problems that we might in the past have spent maybe a whole page on. We'll be able to do in a couple of lines. So in this first theorem, we list some basic rules for differentiation. The first is that the derivative of a constant is 0, right? So think about a function like y equals 5. It's a constant function. Its derivative is 0. That makes sense because a derivative describes how a function is changing, and a constant function does not change. So the derivative of any constant is 0. This next rule, this is really the money right here. We're going to use this so much, the power rule. I'm going to post a separate video of just sort of deriving this formula so we could see why that's true. But this tells us how we take the derivative of x to a power. So if I'm raising x to a power, in order to find its derivative, I'm going to take that power, I'm going to bring it down in front, right? So there's this factor of n there. And then I'll have x to the 1 less power. Subtract 1 from that exponent. And this is something that would have taken at least half a page of work a lot of the time when we were setting up the limit. Now we're just going to use the power rule. The constant multiple rule says we can pull out constant factors from the derivative. So the derivative of c times some function u is c times the derivative of u, right? We could pull out constant factors. And then the last one says we can split up a derivative over addition and subtraction. So if I'm taking the derivative of the sum u plus v, all I got to do is find the derivative of u and the derivative of v and then add them together, and likewise if it were subtraction. So we're going to do some quick examples here, just a handful of these examples to illustrate, practice these rules. So the first function, y equals 5, that's a constant function. dy dx equals 0. There's no work to show, okay? That's it. The next one, y equals x cubed. So here's where we're going to use that second rule, the power rule. dy dx is equal to, I'm going to bring this power down in front, and I have x to the 1 less power, so 3x squared. That's it. There's no more work to show. This is a perfectly communicated solution. We have not skipped any steps. And y equals x. Now, some books like to list a whole separate rule for if you have a linear function, right? Like if your function is y equals kx, then the derivative is k. And that's true, but we don't need a separate rule for this. All we need to do is realize that this is x to the first, and that power rule will do us just fine. So dy dx tells us this will be 1 times x to the 0, and x to the 0 is 1. So this derivative is 1. It's the coefficient on x. All right, let's do some more. In the next example, in part A, we've got the function 3x squared. Now, we know what to do with the x squared. Well, now we're throwing a factor of 3 in front. So we're going to use this third property, this third rule, the constant multiple rule that says, oh, just pull out that factor, that constant factor that's inside. And the way that we kind of see this in action is that dy dx here is going to be equal to, I'm just going to bring the 3 down, 3 times, and then I'll take the derivative of x squared using the power rule. And that is 2, right, bring the power down in front, times x to the first, right, reduce the power by 1. And now I just multiply those two constants in front, so we have 6x. In part B, we've got, now we're going to combine basically all those rules. I've got the power rule at play because I got x to a power. I've got the constant multiple rule, right? I've got all these coefficients I'm going to bring down. And also, I'm adding and subtracting several terms. So I'm going to just take the derivative of each one using our rules term by term, and I'm just going to pull down this plus or minus operations in between. So in this case, dy dx is equal to, so I'm bringing down the factor of 5. Use the power rule on x to the 6th. That's 6x to the 5th. Bringing down the minus, the subtraction here, our factor of 2. Now I use the power rule on x to the 5th and get 5x to the 4th. Bring down the plus. Got to bring down that factor of 4 times, and using the power rule on x squared, we get 2x to the 1st minus, bringing down the subtraction, the derivative of 3, that's a constant, so that's 0. Now I'm just going to clean this up. The first term here, let's see, we got 30x to the 5th. Then we have minus 10x to the 4th plus 8x. Now I've shown kind of step by step how we're applying each parts of the rules stated in Theorem 1 on the previous page. And it can be helpful, you know, if you're practicing applying these rules, I think it really can be helpful to write it out like this, like I did. But after you do a bunch of these, you're probably going to go right from the given function straight to this answer, you know, because in effect all you're doing is when you apply the power rule to a term like 5x to the 6th is you're saying, all right, I'm going to bring the 6 down, multiply it by 5 and get 30, and then I'll have x to the 5th. And so usually after a while of doing some practice, it won't take you long for this to be a one-line problem. There's not really a lot of work to show. And let's see, our last example, we want to find f prime of 1 for this function. So that means we're first going to find the function f prime of x, right? We're going to find the derivative of this function, and then we'll plug in 1. So f prime of x equals, all right, I've got 4 times, using the power rule on x to the 7th gives us 7x to the 6th, minus, power rule on the last term, 3x squared, clean this up a little bit, 28x to the 6th minus 3x squared. There's our function f prime of x. Now they want us to find f prime of 1, so let's go ahead and plug in 1. So we get 25. All right.